Well, hello everyone, and welcome to the first video episode of the HydrogenNowCast. I'm Brian DeBruin, the director of the Colorado Hydrogen Network. And if you're not a regular listener to the audio version of the HydrogenNowCast, I encourage you to do that. As of now, at the end of May 2024, we've got about 85 episodes out there. So I think you'll find something of interest to you. But what I'm going to do from time to time is to record these video podcasts when there's episodes that really need um, slides to go along with them. So what I wanted to talk about today is a cost price analysis of hydrogen and what it needs to be priced at and how we can get to those prices. But first, a little bit of background. To replace petroleum, we've really got to look at the numbers. We've got to set a target price for hydrogen in order to be able to replace gasoline and diesel for transportation at the same cost per mile for the user. And we've also got to be able to replace natural gas for large consumers, things like industry and utilities. And for them, it has to be priced at the same cost per BTU in order to be economical. So the cost of the likely clean sources would include things like electrolysis of water, natural hydrogen wells, which we're starting to hear a lot about nowadays, as well as what I call generated underground or GU hydrogen. And this is a process put out by a company called Proton Technologies. You can see their website there, protonh2.com. And I'm going to talk more about that. So let's define let's let's make sure we have our definition straight before we start. And I want to talk about clean energy, and clean is a relative term. So for the purposes of these podcasts, it has a very definite definition. And then also talk about what it means to be renewable energy. So clean energy obviously would be something that emits no greenhouse gases whatsoever. But then there's also a neutral version of that, which might emit greenhouse gases, but the production of that uh, hydrogen or whatever absorbs an amount equal to the emissions. So it's a net zero. And then something could be greenhouse gas negative, but it could still emit some greenhouse gases. And the definition there would be that the production of that fuel removes more greenhouse gas from the atmosphere than gets emitted in the use of that fuel. Now, renewable energy, of course, means that it's a process that's continually replenished, probably a natural process, but wouldn't have to be natural, and is not depleted. So we could go on forever with this type of energy and not use it up. So it's important to recognize here that clean and renewable are separate characteristics. And I think people tend to use them interchangeably. They really shouldn't, because all renewable energy is clean, but not all clean energy is renewable. And this speaks to the Proton Technologies process, and we'll talk to that in just a little bit. Another example might be nuclear, which, yeah, there's a lot of uranium out there, but it's not inexhaustible. So what about green hydrogen then? I think these terms of clean, renewable, green get bandied about kind of interchangeably, but they're really something different. Now, color was come about to create a shorthand that allows us to specify two parameters with one label. And those two parameters are whether the source of hydrogen emitted CO2 or not, and whether the source of hydrogen was renewable or not. So with two factors with two states each, that's a total of four. So only four colors are needed to describe any hydrogen. And the Colorado Hydrogen Network only recognizes four colors. And those colors are green, blue, gray, which you've heard about before, and then another color, which nobody's even proposed, which we actually need, which is, I'm proposing tan, but I'm not king of the colors here, so maybe somebody else will propose a different color. But the nice thing about tan is it's a color that's kind of recognized in a lot of the primary languages out there. So green hydrogen, it could be hydrogen from wells, underground hydrogen that's generated naturally. It could be hydrogen generated by electrolysis using clean electricity. And this is the one that people usually think of electrolysis as the green hydrogen, but there are others here. And then hydrogen from biomass that has 100% carbon capture and sequestration could be another example of green. All right, so blue, we're all familiar with this. This is hydrogen from fossil fuels that has 100% carbon capture. And good luck with 100%, but that's the definition. And this could be the GU hydrogen from petroleum wells because no carbon ever comes out of the ground in that process. And I'll speak to that a little bit more later. So there's no worry of methane leaks. There's no carbon that has to be sequestered with that process. And then, of course, hydrogen generated using nuclear power. And the reason it's blue is because it's technically not renewable. Now, if you consider it to be renewable, then it would be green. All right, gray, of course, is hydrogen from fossil fuels without any carbon capture. And this was the process that has been used for a lot of years, taking natural gas, doing steam methane reforming or SMR on that, and then just letting the carbon go into the atmosphere. Now, tan, as I pointed out, is hydrogen from biomass that doesn't have carbon capture. We don't really have a color for that, but we really should. So those are the only four colors you need. People keep willy-nilly making up other colors just because they think they have something new, but they don't really understand what the color means. It's just the CO2 or the renewability of it. All right, so the other thing our energy solutions have to meet is three criteria, and I've chosen to use the old three-legged stool here. And the three legs of the stool are technical. We have to have some kind of means of generating hydrogen that's ready for prime time. It's a high technology readiness level, or TRL, if you will. Don't really want to be talking about science experiments here. It also has to meet cost constraints, and I'm going to talk to that quite a bit in this podcast. And then it also has to be accepted by people. In other words, it's got to have the same performance and convenience. If we're proposing, hey, world, we want you to stop using gasoline, we've got to have a solution that has the same performance and convenience that had. So I'm going to talk to all of the functions that fossil fuels provide so that we can look at cost, performance, and convenience of each of these. Now, fossil fuels, we're all familiar with this, but I think it's instructive to take a look at what the functions are that provides, rather than just saying, well, it's an energy source, we need some other energy source. Well, are you providing the same functions? So the functions are, of course, fossil fuels are a source of energy. We dig them out of the ground and you've got your energy. They're also a carrier. You can easily move them around. They can be stored for short term or long term. I mean, nature stored petroleum for millions of years, right? They also have to be able to be transferred to vehicles really quickly. And this is where the battery vehicles really fall down because it just takes a long time to transfer electrons, much longer than it takes to transfer molecules. We also need something that can provide high temperature for industry. And I'll talk to in a minute, there's actually some other characteristics besides just the temperature that fossil fuels provide. We've got to have something that can be sent long distances, either across continents in pipelines or across oceans in tankers. And it also has to have a high energy density for things like long distance aircraft flights, as well as for ships. All right, so what do we have? Excuse me, what do we have that can be replacing these things? Well, we all know about wind and solar, and we'll increasingly hear a lot about geothermal because the nice thing about geothermal is it runs 24/7, right? It doesn't stop like the wind and the sun does. But that's really only an energy source. All right, so what can we add? Well, we've got the electric grid. That's a pretty good carrier. Long distance, at least over continents. Some people have proposed wires under bodies of water if it's not too far, but you really wouldn't send it across the Atlantic or the Pacific. So we have batteries, of course. They are an energy carrier, and they're pretty good for storing short term, although they're expensive. But they're terrible at long term because all batteries self-discharge. So eventually they'll go dead even if you're not touching them. And we're all familiar with that. If you keep some batteries in a drawer for a number of years, they'll eventually be dead. So if we add hydrogen, now we have something that's an energy source. And as I already talked to, that's things like hydrogen wells, the GU hydrogen, the generation underground hydrogen from petroleum, and then also hydrogen from biomass. So you'll hear people say, well, hydrogen is a carrier, it's not a source. Well, sorry, they're wrong. They're not keeping up with the times. It really is a source of energy. A very good carrier, can be stored short or long term. And really, really importantly for transportation, hydrogen can be transferred quickly to vehicles, which batteries can't because it's not a function of the battery. It's a function of how much energy you can apply to a vehicle. And it just takes a long time to transfer that much energy using electrons. Now, hydrogen can also be used for creating high temperatures for industry, but there's more than that. Those of you that are familiar with steel making know that one of the processes of steel making is to remove oxygen from the ferric oxide, or basically rust. And the way that's done with coal and coke is that those contain carbon, and the carbon combines with the oxygen and forms carbon dioxide and removes that. Well, you can do the same thing with hydrogen, but instead of the oxygen that's in the rust combining with um, uh, carbon, it combines with hydrogen basically to form water. And so that helps to remove that oxygen from the steel making. And of course, hydrogen can be used for long distance energy transport, either pipelines or in tankers across oceans. Now, what we're missing here, though, is something with high energy density. Hydrogen, it's tough unless it's a liquid, which is a little bit complicated for ships and planes. So we still need a piece. So what could it be? Well, I'm proposing that we're going to need biofuels for these high energy density applications like ships and planes. Now, it's clean and renewable, but it's not zero emissions because we are using the atmosphere to exchange that carbon dioxide between the source of creating that biofuel and then the user. So it basically exchanges or uses the atmosphere to exchange the CO2. All right, so what's a good example of a biofuel? Now, uh, anything that's a hydrocarbon could be used. Certainly sewage or garbage or old plastics and whatever. But if we want to really look at something specific for this, algae is a really good solution because it doesn't have, there's no waste as far as removing CO2 from the atmosphere. It's all photosynthesis. There's no stems, there's no roots, there's no bark, and things like that. Now, the other nice thing about algae is it can be very easily converted into three products here that make this really financially viable. You can create industrial enzymes, you can create animal feed, although if we do this at very large scale, you probably saturate the market for animal feed. But really importantly, it can be easily converted into a biocrude. Now, that biocrude could be run into a refinery and created into other products like we do today, or we could sequester some of it underground. So, for example, let's say you have an algae farm and you're producing this biocrude. Well, you could either be told to or pledged to sequester 10%, 20% or something of that biocrude underground, which would actually make this process somewhat carbon negative, even though we're using the atmosphere for the CO2 exchange. So the bio crude goes into a refinery. It could be made into almost anything you want: diesel, JP4, the jet fuel, renewable natural gas, methanol. And then those biofuels could be really useful for long distance aircraft, for existing home heating, because it's really difficult to change out all the furnaces that are deployed out there. Or it could be used for shipping, where you need a stable, safe, high density um, fuel. That CO2 from those processes would go back in the atmosphere, and then the process would repeat. So we as a society may at some point decide that, well, we really have to have some kind of biofuel for these really hard to decarbonize sectors like long distance aircraft, existing home building heating, and shipping. And by the way, I think for new build, whether it's commercial buildings or homes, heat pumps are the way to go, but so expensive, $10,000, $20,000 to convert existing homes, heating plants. And then you have situations where heat pumps may not work that well. For example, I live at 8,000 feet. It's a fairly cold climate here. because of the elevation and everything else, heat pump, at least with today's technology, is problematic. All right, so if you want to learn more about this, I encourage you to go to two audio episodes of the Hydrogen Nowcast on April 29th, 2022 and February 10th, 2023, where I interview Richard Sayer, who is a scientist or was a scientist with Los Alamos National Labs and has really pioneered developing these algae strains. And this really, according to Richard, at least is ready to go, ready for prime time. All right. So if we're going to talk about using hydrogen, obviously the hydrogen needs to be clean because if it wasn't for the need to eliminate greenhouse gases, I mean, we wouldn't even bother with hydrogen. We just happily keep using fossil fuels. So the sources of clean hydrogen already talked to electrolysis of water, natural hydrogen wells, and then this so-called, I'm calling it GU hydrogen or generated underground hydrogen with the proton technologies process, and encourage you to go to their website, which, by the way, they have a new website. So if you've been to their website before, you may find that the old website doesn't work, but the new one is protonh2.com. All right, so let's take a look at a gasoline and diesel replacement, and let's try to derive a price for that. So we kind of know what our target is. So our goal is to price hydrogen, which provides the same or better cost per mile as petroleum. And this would enable any user out there to switch without having to pay a premium. Now, the cost per mile is based on vehicle efficiency, which I'll talk to a little bit here. But although hydrogen vehicles are more efficient than petroleum vehicles, that does vary by class. So we've got to look at whether we're replacing a gasoline or a diesel vehicle and what some of the uses and the sizes of the vehicles are. So to help us do that, the California Air Resources Board has published what they call the energy economy ratio, which is a ratio of miles per kilogram to miles per gallon for similar size and weight vehicles. In other words, if you had a vehicle that was similar to a Toyota Mirai but was gasoline, comparing your cost per mile for that gasoline vehicle to your cost per mile for the Mirai, which is a Toyota hydrogen vehicle, you would have this ratio. So here's a table that shows in the center there the EER for these different vehicles and the different classes. And here the LD is light duty, MD is medium duty, and HD is heavy duty. So assuming some cost for the petroleum, and I just use what the prices are at this time in this area here where I am, and then multiplying times that EER, that tells you what your price at the pump has to be for your hydrogen so that these other users that are converting from a light duty gas or a heavy duty diesel, what they would have to be buying hydrogen for in order to get the same cost per mile. So you see there's quite a variation there. But that's important to know. So just be aware, and especially for the high density, or I'm sorry, heavy duty diesel versus local versus highway, there's a big difference there. And of course, on the highway, those vehicles are almost like towing a parachute, right? They have a lot of wind resistance, and that's part of why the highway efficiency is a little bit lower. All right, so next, let's look at what it would cost to get hydrogen from some source to these fuel stations, because we've got to add that on to the source cost. So I looked at, just as an example here, a 50-mile delivery zone using liquid hydrogen, liquid organic hydrogen carrier, the LOHC, or using ammonia, or comparing it to on-site electrolysis. Now, the reason we would convert hydrogen to a liquid or combine it with something to make it a liquid organic hydrogen carrier or make it into ammonia is that it takes up a lot less space to store and to transport that hydrogen in those forms. Now, you have to convert it, and you have to convert it back. So does the savings in your transport make up for the cost and energy to make these conversions? And usually it does. So I wanted to look at what the capital equipment, the CapEx, is for each of these systems, because I'm assuming that we're starting from nothing. that there is nobody out there we can buy hydrogen from, that we've got to find a source like a hydrogen well, and then we've got to convert it to liquid hydrogen or convert it to a liquid organic hydrogen carrier. And what does that equipment cost to do that? And that's what these represent, as well as the truck and the reconversion equipment. And then obviously we have investors that are going to help us pay for that capital equipment. So what do we have to pay them back? And the assumption that I made here is that after 10 years, you would return twice the value of that investment. So for example, the 3.8 million would be, what is that, 7.2? No, I'm sorry, 7.6. I'm drawing a blank there for a second. So we'd return 7.6 million after 10 years. And that's what that debt service signifies. Then obviously there's some operating expense, things like electricity, or maybe just some of the costs of operating the plant, and that's covered there. And that sums together to a transport cost. So the $2.40 and the 204 in the first line there sum up to $4.44. So if we assume that we've got a source of hydrogen, either a natural hydrogen well or the Proton Technologies process of underground hydrogen generation, that produces 30 cents all in, OPEX, CAPEX, the total cost of that hydrogen from our theoretical source to the pump is this, all right? So let's compare that. I already showed you what the price had to be, and then this is what our cost is. So which of these are economically viable? So we make up a cost price comparison table in the lower right there, and the check mark is the box where the price that we can sell it at, that's satisfying the user, is greater than or equal to the cost. So you can see that for our theoretical source at 30 cents a kilogram and using liquid hydrogen, we could satisfy any of the vehicles out there, the light duty, medium duty, heavy duty, whether they were a diesel user or a gasoline user. Now, it's a little bit of a stretch on the heavy duty for highway, although I suspect that if you could get some economies of scale going here and some other things, you might be able to reach that $4.40 a kilogram level. So you can see we've got a number of options here, and electrolysis will work for light duty people switching over from gasoline vehicles. And so that's kind of an interesting point because, everybody out there is saying, oh, heavy duty diesel vehicles, that's hydrogen's sweet spot. Not really. That one's actually a little bit of a stretch, but certainly for light duty, we can satisfy the business case in any case. So takeaway here is that our hydrogen source needs to cost less than 30 cents per kilogram at the source. And certainly Proton Technologies believes that their method of creating hydrogen can do that. Now the catch is, in order to achieve that price, you've got to sell a lot of it. It produces a lot of it, but you got to have a user. And so that kind of brings us around to looking at natural gas users. All right, so what does our hydrogen have to cost? What is the price? I'm sorry, what does the price have to be for our hydrogen to satisfy these natural gas users like commercial users and utilities? Well, right now, the natural gas cost per 1,000 standard cubic feet is $9.60. Now that embodies 922,740 BTUs, and each kilogram of hydrogen has a BTU at the lower heating value, the LHV, of 114,887. So if we divide the 922,000 by the 114,000, that's a multiplier of about 8. So 8 kilograms, 8.03 kilograms of hydrogen is roughly equivalent in BTUs to 1,000 standard cubic feet of natural gas. So if our price was $1.20, we would satisfy those users. They would be happy to pay $1.20 for a kilogram of hydrogen to replace natural gas. All right, so on the cost side, well, we're expecting to get hydrogen at about 30 cents per kilogram, either at a well or at some other underground source. But in order to get it to those utility and commercial users, we'd probably have to have a pipeline because the quantities are just too great to move it by truck. So, assuming some fairly short point to point, small diameter pipeline to get between a well and, say, a utility hydrogen or electric generator that's burning hydrogen, we'd have to have the operating expense plus the return on investment, the OPEX plus the ROI, in the 20 to 80 cents per kilogram range, which would help us compete with natural gas. And I think that's certainly doable. So in that case, the cost is less than the target price. So the hydrogen really could compete with natural gas as long as it's at the source priced at under 40 cents per kilogram. All right, so the takeaways are that hydrogen can compete with petroleum for transportation. On-site electrolysis is competitive with the previously light-duty gasoline vehicles. For all other classes of vehicles, we probably have to have this 30 cent a kilogram source, like natural hydrogen wells or the GU hydrogen. And liquid hydrogen is probably the lowest cost and the way to transport that. Now, hydrogen can also compete with natural gas for industries and utilities, as long as, again, we can come up with a source that's 30 cents per kilogram or less, which absolutely we can in Colorado. There's other states, of course, that have no oil wells or may not have any natural hydrogen. We don't know yet. The search hasn't been done everywhere for natural hydrogen. We'll probably need pipelines to be able to distribute it at a reasonable cost because the quantities are just too great for transporting with tankers. And probably 20 cents to 80 cents for the pipeline is reasonable. All right, so let me give you, as kind of an aside here, just a little bit of information about this underground hydrogen generation. What I'm showing here, the gray cloud, is some kind of a petroleum reservoir. What you do is you inject oxygen into the well, which reacts with the hydrocarbons and the water and starts to free up hydrogen in something that's called a fire flood effect. And this has been known for years with the oil industry, so this is nothing new. So this causes hydrogen to be released underground, and then that pure hydrogen is brought out of the well through a palladium filter, which allows only hydrogen. As a matter of fact, it's 99 and 4 nines, so 99.9999% pure hydrogen coming out of the well. So we, again, have no concerns with methane leaks, with carbon that's been brought out of the ground to sequester. And so it's very safe. This works really well with abandoned spent wells because you want a well that's still got petroleum in it, but also has water and other things. And by the way, the oxygen that's fed into the well helps you control the pressure that's in the well. So there's no problem with overpressuring. You're pressuring it just enough to bring it out of the ground. And certainly once you stop injecting the oxygen, the pressure is going to drop. So no worries about leaks or blowouts or driving these elements somewhere else. Now, one other really nice thing about this is that this process can sequester 3 times the carbon dioxide as the hydrogen that's generated. So if you bring a ton of hydrogen out, you can inject 3 tons of carbon dioxide, and that will combine with the rock that's underground and remain locked down there. So not only is this zero carbon, but it's actually carbon negative because of that. All right, so if you would like more information on this, I'd encourage you to go to the Hydrogen Nowcast in December 23 of 2022 and hear an interview with Proton Technologies to find out more information about this. So one last thing, I wanted to show the petroleum wells in Colorado. The blue dots here are abandoned wells. There's over 20,000 of those in Colorado. A lot of these wells are near utility electric generators, so it's only a distance of a couple of miles to run a pipeline from one of these wells to one of those hydrogen generators. And that's something that I'm ongoing with, trying to get the utilities and the oil industry interested in teaming up to do this. All right, so that's it for this cost price analysis. I hope you find it interesting. I hope you've got some good data there. Um, Here you can see the website for the Colorado Hydrogen Network. You can reach me through that website if you'd like to, and encourage you to go to your own favorite podcast app and listen to the Hydrogen Nowcast. Subscribe, give us a listen, and to give us a like. All right. Thanks, everyone.